try to get through everything that you need to do for the labs. So I'm going to try to ask a few questions, but we're not going to have time for very much. So basically, electromagnetic induction is a way of looking for electrical conductivity or resistivity, but it's a very, very different experiment. And it's one, as I said, that you're used to if you went through airport security. The following things are happening. We've got a source over here which gives a time-varying magnetic field. A time-varying magnetic field generates an electric field everywhere. So we've got something that looks like this. So if I have something that is time-varying magnetic field, it gives an electric field everywhere. And if I have an electric field, then I've got a current depending upon my conductivity, and then so that's going to give a current that's in here, and then those currents are going to give rise to a magnetic field elsewhere. So the formula for that is curl A is. So those are the three steps. It doesn't matter if you know how to manipulate these things or not, but this is a way that I can kind of converse with you and telling you what's happening. I have a time-varying magnetic field that gives me an electric field that's got a current, so it's circular. I've got an electric field and a conductivity that gives me a current. I've got a current that gives me a magnetic field that's also circular. So that's the verbiage that we work through. And we can have it at a mine detector or metal detector or something like that. The picture that I didn't show yesterday, which is kind of interesting, is that the physics that we did for this guy doesn't change at all. We can just scale things up. This is the beautiful thing about electromagnetics. So here's an example where we now have a transmitter that's mounted on a plane, and we're looking for a big body in here. Same thing. Time-varying magnetic fields generates electric field. If there's ever any conductivity there, we get currents. Those currents give rise to magnetic field. Same process, small scale, big scale. So this is kind of how we sort of set things up with the basic experiments, and then the motivation, especially for airborne, is that we have these really large areas that we want to cover, and so we're going to fly the plane up in the air. So in this course, we're actually going to use some stuff that's on the ground, and I'm going to talk also a bit about the airborne as well. So the physical property was the electrical conductivity, which we've done a fair bit, and the basic principles, we're going to step through this thing right now. So the very first thing is that we're going to have as our kind of signature experiment here, like a helicopter. It's going to be towing a bird that has got a transmitter on it, and that transmitter is going to give rise to a magnet. Here. So let's just look at a little bit more at that. A transmitter is nothing other than just a loop of current. So we somehow have a current that's going in here. It's connected up to a generator, and that gives us a primary magnet. We talked about currents and magnetic fields. Remember, if I have a straight wire, then that gives me a circular magnetic field that goes around it, and that's the formula for it. If I take this wire and I bend it in on itself, make a loop like this, then each part of this, if I look really close here, it just looks like, well, okay, it's a little bit of a circular magnetic field. It's kind of a circular magnetic field. In the end, this whole thing actually gives rise to a magnetic field that looks like this, and in fact, it is the magnetic field of a dipole. When we were talking at the beginning of this course about magnets, we talked about the strength of the magnet. When we convert that to this formulation, the strength of the magnetic magnet or the magnetic moment, M, is the product of the current that's in the loop times the area. So the bigger the area of the loop, the stronger the current, the bigger the magnetic moment is, and that, just think about like, okay, I got a bigger magnet. Okay? So that's that relationship between magnetic moment and currents. And remember, this is the same formula that you saw earlier on. Yeah? Sorry? Oh, this is a theta, so that's just the phi. Oh, I see. So phi is the circular. So we've got something that's like this. So this is theta in this direction, going in and out of the board, and a circular manner is phi. So then this is Faraday's law. So that's what I first wrote up here. And it's basically like this. And as I said, you don't really need to manipulate these things. Just think about these things as being words. So this is time rate of change of the magnetic field. And that gives rise to an electric field everywhere. Okay? There's an important thing here, and that's a minus sign. You're going to see that coming into things a lot. Basically, it's the system that the Earth, if these currents are going to be created, they're going to go in a particular direction. So that's the question, okay, which direction are they going to go? The direction that they're going to go is one in such a way as to oppose any change in the magnetic field. In other words, so suppose Samantha is our conductor. I got to put a time-varying magnetic field on her like this, right? And let's suppose that field is increasing. Then at her position, she doesn't really like the fact that that magnetic field has changed. So there's going to be currents that are going to be generated. And in this case, those currents are going to go counterclockwise so that when I use my right-hand rule on it, the magnetic field from those currents come out towards me. So they're opposing the change. So that's an important part. So we can easily see that, okay, a time-varying magnetic field is going to give circular electric fields. Okay, so I'm going to have circular currents. But which way are they going? Well, they're going to go in such a way that they're going to oppose any change. So the magnetic flux is increasing. They're going to oppose. So we can see that here, and you're probably familiar with this. You probably did this in first year. So this is what we've got. We've got a coil of wire, and it's all going to be hooked up to a circuit. So we're going to measure the voltage, and there's a light bulb that's on here. So if we ever get any current that goes through here, there's going to be a light in our bulb. So right now, I've got a magnet sitting just like this. I got a north pole and a south pole. And you remember which way the field lines go? They go from the north pole to the south pole. Right now, everything is static. So there is a magnetic field here everywhere, but nothing's changing. So if I look to see what's happening here, it's a complete nothing. Nothing is going on. Just to plot things out a little bit more in detail, so here's now the magnetic field lines that are going like this, okay? And I'm going to introduce something called the magnetic flux. So B, if you remember, or if you notice when we're talking about it, B was magnetic flux density. So magnetic flux density, and it was Weber per meter squared. If I take a loop of wire, and if I put a magnetic field through that, okay, so now I put some magnetic field through here, then if I've got a particular area A here, then the total flux, which we will call like that, is the integral of B, and then I want just the normal components, so n hat, so that's how much is actually coming through, times dA. And in this particular case, if this is perpendicular to the plane of the loop, then now my flux is just equal to B times the area. So this is 5D. So it depends upon the orientation of the magnetic field with that loop. The left-hand side of this equation, which is Faraday's law, if I write the whole thing, this whole thing as a circuit diagram, I've got a resistance here with my light bulb. I've got a coil, so it's got a self-inductance to it. And the Faraday's law says that the voltage that's going to be induced in here is equal to minus d phi v dt. So minus the time rate of change of the flux. So right now, if I look at this thing, nothing's happening. So there's no time rate of change. There's a flux, but no time rate of change. So everything looks like that. However, if I take this magnet and I push it in, okay, so now I'm going to push the magnet in. So the strength of the magnet is going to get, high strength is going to get close to the coil, so I'm going to be increasing the flux. So if I'm going to be increasing the flux, then that means this quantity is not going to be 0 anymore. I get something that looks like this. So my magnet goes in, my flux is increasing, so d phi b dt increases. But then I got this minus sign here, so that says that the voltage is less than 0. So that means it's flowing in one direction. Okay, so that's what's happening. I take my coil, or my magnet, so doggy's the coil. I push it up to it. There's a time-varying flux. Okay, the current opposes it, and now there's a current in there. If I now take this magnet away, what's going to happen? Anybody? Arnold? What?
So it'll be the V will be positive sign because it's going in the direction.
Yeah. So now if I pull the magnet away, so now there's less flux. So I'm changing the flux, but I make it go from big to small. And now this quantity is actually going to be greater than 0. So now my voltage is plus, so the current's going this way. So back here, in this direction, okay, the current goes one way, and back here, it's going, Okay, we have a couple of apps. There's one that does it in the time domain and one that does it in the frequency. So this is the simplest of the apps that we can generate. It's a 2-coil app. So there is a primary magnetic field, or there's a primary coil that's generated by this guy here. So it's going to generate field, and then we're going to have that impinging on a target loop that has got a particular resistance and inductance. And then we can see what the currents are going to be, right? So just to say this again, so we're going to have a coil up here. So this is going to be a primary, and then we'll have, let's say another coil down here. So here's going to be our target loop. And if we change the current in here, that's going to change the magnetic flux that goes through here, and that is going to change your induced current. So you're going to be able to experiment with this. I'm not going to take you through that too much, but I'm going to show you a diagram. And then you can also move this target. At this point, what I simply wanted to do was to to take you through the following steps. So let's suppose in our primary loop out here, we've got a current. So now this current comes here, so there's a primary magnetic field that's coming vertically down. And if our primary current is on and then we turn it off, then it looks like this. So this is the primary current as a function of time. So keep time over here. It's on, I turn it off. Magnetic flux has a constant value when the current is on. The moment I turn the current off, then there's no current, there's no flux. Okay? So there's. But what about the time rate of change of flux in this target loop here? Well, instantly there's a huge time rate of change, right? So it's like a delta function. It's like an impulse. And that's going to immediately set up a current in here. And that current is then simply going to decay, just the way as if you initiate this circuit here with an initial current, and then you just let it go. And so that current decays away according to this formula here. So this is, so the secondary current, that's the current in the target, is equal to some initial value. That's what happens right when you turn this thing off. And then e to the minus t upon tau, where tau is equal to R over L. So remember, we've got this circuit like this. It's got a resistor, and it's got coil, looks like this. So this is L, this is R, and there's my voltage. The moment that I turn this thing off, then there's going to be a current that's going to flow in here, and that current then decays with a time constant, tau. This is called a time constant, and it's the ratio of the resistance of the circuit to L itself. Yep.
You've got L over R up there, R over L on the board.
Oh, yeah, L over R. Okay, so the smaller the resistance, okay, so which way is this going to go? If I make the resistance small, then what happens to tau? Get bigger or smaller?
Bigger.
Going to get bigger. So if tau is bigger, then how is this thing going to decay? Is it going to decay slowly, or is it going to decay quickly? Pardon me?
Slowly.
So if tau is large, right? Yeah. So then this number is going to be small, so it's going to then decay really slowly. So a good conductor is going to have a slow decay. A poor conductor is going to decay. So that's what's shown up here. We've got different kinds of conductors, so they have different taus. If tau is large, then it kind of decays slowly. Tau is small. Okay, so let's just make sure we've got that consolidated now in the time domain. So R knows a coil, okay? I put a time-varying magnetic field on here, and I'm just going to stop it. So I've got a magnetic field, it's constant, I just turn it off. The moment I turn it off, there's going to be a response current that's generated in you that's going to oppose that change, and then that's just going to decay away. So that's the basic physics. We could do that, yeah.
You go back and mention the difference between response function equation versus IST.
Oh, well, these things here they're plotted on different scales. So this is a linear plot. So this is this e to the minus t upon tau, right? It's going to go like that. So that's a response function. But these things here if I plot it on a log plot and linear, then they look like that, right? So if I take the log of this thing, so if I take the log of this, so I got log IS, well, minus G. So that's a linear. Okay, so that's what happened if we took this coil. So again, here. So here's our primary coil, right? So it gives magnetic flux that goes down. So if I had a target moved in here, so this is, so here's my target, and this is R L. So the magnetic field for the primary loop is going to be, just like a magnet coming down like this, so that the magnetic field comes straight down. If my primary current is a constant and then I turn it off, then in here I'm going to get a current Is of t, which goes as e to minus t. Okay, just. But what happens if I do something a bit different, and instead of having a current that looks like this, I should have a current that looks like this. So now it's going to be a harmonic current, right? So that complicates things a little bit, because now, like, there's always a time varying change of magnetic field in the coil, so I'm going to have to somehow keep track of that. So here's what your second app is, and it's for what's called a harmonic. So that means just a sinusoid. So it looks like that. So now in our primary circuit, we've got this harmonic field, and so the field on here is going to be changing. So let's just kind of parse that out a bit, and you'll play with this app this afternoon, and you're going to be looking at all of the pieces that are here. So I'm going to try to explain them really, really carefully. So let's start with the primary field. So I got a current, and it's just the oscillating current. So it looks like this. So it's the amplitude of the primary current, that's cosine omega t. Okay. If I have a current, so now you can imagine a primary current or a primary magnetic field, so it's impinging on Samantha. So it's harmonic, right? So it's just got a particular frequency that's associated with it. Inside her, she's going to have currents that are generated in response to that time-varying magnetic field. And the question is, like, what can they be? They can't just be like a decaying thing that we saw in the time domain, because the magnetic flux is continuing to change. So they have to oscillate. So if the currents inside Samantha are oscillating, it's a particular frequency. But what frequency can it be? The only frequency that it could be is the same one as what the input current is. Okay, so that means, first of all, whatever current is flowing in Samantha, it's harmonic with the same frequency as the primary. So what can happen? The only two things that can happen is, okay, there's some amplitude of that current. So let's suppose that the primary current, was 2 amps. Okay? Well, the secondary current, going to be something different. Maybe that's 0.5 amps or something, right? So that's one thing that could change. So I go from the primary to the secondary. That's the amplitude. And what's the other thing that could change?
It can lag.
Yeah, it can lag, exactly. You guys are all engineers, you know about that. Okay, so the secondary field or current, varies as cosine of omega t minus some phase angle. Okay, so it's changed in phase. Yeah.
What's omega?
Omega is frequency, so it's 2 pi f. So omega is angular frequency. Is that? Yeah. Anybody surprised at that? I think Sagi talked about this when he did the GPR. So now we got this guy, okay? Well, what do we do with him? You remember cosine? If I, for first year math, if I had cosine A minus B, right, is equal to what? Help me out. But nobody's bringing their cars. Do you see how many of this stuff I got? What am I going to do with this, right? Al, Stefan, only grab when you have a car. Okay. Cosine A minus B, and only if you have a car. Okay, so it's what? Cosine I mean, I always have to look whether it's plus or minus, but this one is sine A, sine. Okay, so that's your basic relationship. So now we can take this thing. We have cosine omega t. So we've got I-S cosine omega t minus psi, which gives us I-S cosine omega t cosine psi plus I-S sine omega t sine. Okay, so we're doing fine. So let's just kind of regroup this. So this is an I-S cosine omega, that's cosine omega t, plus I-S sine omega, sine omega t. Okay, so what do we got? So I got an oscillating current in Samantha, and it's harmonic. It's lagging the primary field, but I can actually break this down. Okay, so this is the primary field, right? Then I've got a part of the current in Samantha that's exactly in phase. Okay, so it's going like that. It's got a little different amplitude. That's really hard. Okay, there we go. I'll do the same amplitude. Okay, so it's part of it that's in phase. Okay. And the amount of that is just given by this quantity here. It depends upon the phase. So IS. Okay? So I've got a part of it looking like this, right? And then I've got another part that's out of phase. So it's 90 degrees out of phase. This is really tough. It's kind of goes sort of like that. Okay? So I got a part that's in phase. I got a part that's out of phase. And I'm going to add those two things together, and that's going to describe the total. So this is what we have here. So I've got a primary field in red. So here's our primary current. And now the secondary current looks like this. So you see it's got a different amplitude, but there's also a phase shift. You look at the peak here, look at the peak here, they're different. Okay, so there's a phase shift inside. That phase is given by the following. It's pi by 2, and then there's an arctan of omega L upon R. So remember, L upon R was this thing that we were called the time constant, and omega was 2 pi f. So I could take this green curve here, and I could decompose that, okay? So this, whatever psi is, I choose this guy here, and that's going to be the amplitude of the green. And then I take this guy, and that's the amplitude of the out of phase. And the thing is, if I add these two guys together, I get the green. So we're going to call these things, and here's, unfortunately, a potential source of some confusion. But just the same as we interchange resistivity and conductivity, we're going to call these two things by different names, and you just have to get used to it. So there's a part here that's cosine omega t, and that is sometimes called the in-phase part, right? So we kind of got that. That's the in-phase part. It's also sometimes called the real part. And the reason it's called the real part is mathematics is usually done in complex variables, and so there's a real factor. So that's what we have here. This part is called the outer phase. It's also called quadrature, because quadrature means 90 degrees shifted. And it's sometimes called the imaginary. So what I want you just to get used to is that if you see in phase or you see real, they're the same things. If you come over here, you see out of phase, quadrature, or imaginary. It's just 3 words for exactly the same thing. And you get people, myself included, who just, we just use them interchangeably. We try to be consistent. Like real and imaginary is one, but sometimes that doesn't mean as much to people. So we try to use in phase and quadrature, but not consistent. So just kind of memorize those words. So what this does, okay, is sort of partition the secondary current into a kind of an in phase and an out of phase component. And the quantity that's important is this alpha here, mentioned back here, omega L upon R. And that's called the induction number, because we're inducing stuff, right? So this is the induction number of the circuit. And depending upon whether that induction number is small or large, we get different kinds of partitioning. If alpha, induction number, is really small, then most of the response is actually in the out of phase part. If the induction number is large, most of it is actually in the in phase part. And so you have this curve here that kind of tells you how much of that response is in the in phase and how much is in the out of phase as a function of induction. This is an important plot to remember. You're going to see this time and time again because it contains so much information, and it helps you really understand what's going on. I'm going to give you a case history, work that we did many, many years ago on the Expo labs. After Expo 87, might be a little before your time, the area was found out to be a little bit polluted. And so one of the techniques that was used was a frequency domain EM system that went over the regions, called it EM31. And that instrument collected both the in-phase and the out-of-phase signal, and we're actually able to use that to find both pipes and hydrocarbons and stuff like that. So we're going to unfold all of that into a little bit of this week's lab, but then also to a next lab where we're going to be working with that.
Josh.
Oh, Josh, yeah.
When the induction number equals 1,
yeah,
and the in phase and out phase they align, they intersect.
Yeah.
Does that mean that your out phase and in phase curves look the same? Like, are they identical, or like what does that mean?
Yeah. So if it was 45 degrees, then the amplitude here would be the same as the amplitude here. They'd still be
Shifted.
Right, they're still shifted,
Yeah.
right? So what this is doing is telling you the relative amplitudes of how much is in the in phase and how much is in the out phase. So that's basically it from the point of view of thinking about a two-coil system. Okay. We've got changing primary field on here. It's going to induce currents, and those currents are going to be in a frequency domain. Some of it's going to be more in phase with the primary than others, and that's going to depend upon the properties of this target. In reality, however, what we're going to do, let's see. Oh, maybe I'll just carry through one more slide. Okay, so what this is, time-varying magnetic fields, so that's going to generate a current in here. And now we've got this, now we want to carry that current back to a receiver, so that's what this is. So that was Ampere's law. If we have a current, then that gives us a magnetic field, but also this. Okay, so how do we measure this stuff? Well, we can have a magnetometer, so we can have a three-component magnetometer that measures the three components of the magnetic field, or what you guys did when we started this course was to use a total field magnetometer, so it measured the amplitude. But you could actually measure all the components. The other is that if we had another coil that was sitting here, so now we got, so Samantha's got secondary fields, okay, they're time varying, right? Some in phase, some out of phase, and they're coming up to now another coil here. That time varying magnetic field is going to generate a voltage in this coil. Okay? So that actually is going to be how the whole system is working. We're going to have two coils. We're going to have a coil for transmitter, okay? And then generate some currents, and then we're going to measure the strength of those by measuring the voltage in another coil. So it's like a three-coil deal. So here's an important aspect here, and it's all called coupling. So let's first of all think about that two-coil system that we're working with. So here's the transmitter. The magnetic field from that transmitter just looks like a dipole, looks like that. Suppose I have a coil that's sitting right under here. So imagine this now being the target, right? So now I've got a target that's sitting right under there. Look at the flux, right? It's just coming smack down. So I've got, you know, the maximum amount of flux I can possibly get that's coming through that, just the product of the E times the area. However, suppose I had a coil up over here. So now the magnetic field is like this, and I've got my coil like that. How much flux do I have going through there? No. So what's going to make a big difference here is the orientation of the magnetic field. So suppose I got a transmitter loop, and now I've got a magnetic field that's coming down like this, right? So if this is my other coil, and if it's sitting just like this, I've got just a huge amount of flux coming through. If I turn that coil like this, I don't have so much. And if I turn it like this, I don't have any flux coming through. So even though I still have a time-varying magnetic field here, if I'm not coupling properly with this target, I'm not going to get any currents in here. So this whole business of how your target kind of interacts with the orientation of the magnetic field is called coupling. And we want to maximize that always. So that's what we're seeing here. You've got different examples of coupling. So here's my transmitter, here's my target. That's perfect coupling. If it's sitting over here, I don't have anything. It's like null coupling. And if it's sitting someplace else, I got maybe water. So you'll be able to explore that also with the app. Yeah.
Sorry, when you say that that's the target, do you mean that's what you're trying to observe?
There's two aspects here, but generally when I say target, that's what we're trying to observe. So that's your ore body or your iron pipe or whatever like that. This diagram is actually more general than that, because now we could imagine that this guy here, okay, now he's the currents in Samantha, and we've got to get that information over here to another loop, and I've got to orient that properly.
Okay.
So there's two levels here. So this is the initial transmitter, and here's your target, okay? And then the next thing is like, well, same diagram holds. If I thought of that as being my currents in my target loop, and then here would be my receiver, I still have that same kind of coupling. So that actually allows us to put together the physics on a slide that at first sight might seem a bit complicated, but in fact is actually really understandable. And here's how we're going to do it. So our general idea about a geophysical experiment for electromagnetics is as follows. We got a transmitter, put energy in that. We got a conductor in here that we're going to get these currents. I never mentioned this word, but sometimes those are called eddy currents. So induced currents, eddy currents, again. So we get these currents that are inside. Those currents give rise to a secondary field that could be measured at the receiver. I told you that everything depends upon coupling, and here's how we could define it. So let's place these three guys here with three loops. So here's our transmitter, loop, and we'll represent our target body by another loop, and our receiver by a third loop. So now let's think like, okay, how would we understand this guy here, this guy here, and here's our target coming down like this. So this is, let's call this loop 1, and this loop 2, and that loop 3. So here's our transmitter, and here's our target. So first of all, if we're just kind of thinking about strengths of things, we're going to have to know how this loop and this loop couple together, right? So we're actually going to use that as like a geometric factor. It's called the coupling coefficient. It could be evaluated like that. But let's just think about M12 as just how this loop couples with that. You know, are they perpendicular, or are they planar, or whatever else? So that kind of tells you the strength of the inducing fields as they're getting down here. And now we get these currents that are going in here, they're going to generate a magnetic field, and they need to couple with this receiver. So if you thought about, okay, the amplitude of the signal at the receiver that's coming this way, it's got, first of all, a coupling coefficient to get down here. And it's got another coupling coefficient to get up here. Now that could be compared with the amplitude of this direct wave here, the primary field, which is the coupling between this loop and that loop. So that's M1. So these terms here, you can understand geometrically, you just physically understand them. They're just have to do with this coupling. And then there's all this stuff over here that involves this induction number, and there's I, the square root of imaginary number. I think you guys aren't overly. How many people do you actually work with, like e to the I omega t, and the fact that I is the square root of -1? Just one? Yeah.
That a lot in first year. It takes not so much in geo.
Yeah, okay. Anyway, so it doesn't, just think about this guy here as being this response curve. Okay? So now you got it. This is kind of cool, right? Because what we're really interested in is what is the ratio of a secondary field that comes this way to whatever the primary is. And if we could get that, that would be valuable information about telling us what's there. And so here's the final formula. It looks something like this, and then there's a response curve that is telling us. Yeah?
Just how that the conductive body at depth is not work there.
Yeah.
And it's not because it's not like oriented to shapes like a current, and say it's like isotopically conductive inside. Does it matter what the? Does that make sense?
Yeah. So the shape of the body actually does matter, and at some point we need to really take all of that into consideration. For the point of view of kind of getting the concepts down, these little coils actually work. So now we got to do one more thing. Let's see. Okay. So here's the scoop. Because you'll do more of it in the lab. So let's first of all think about what's going on. So we've got a transmitter and a receiver. And let's suppose that they're both on the left-hand side. Okay? So I've got now a magnetic field that's going like this, so that's the blue, that's the primary field. Okay? So let's suppose that's changing. And now, just as we talked about, there's going to be an induced current in here. Okay? There's going to be a current in here to oppose that. Okay, so that means that my right-hand rule says that the current is going to go clockwise from this direction, and the magnetic field from that is going to go like this. Okay, so the red parts are the secondary magnetic field. Okay, all that right-hand rule stuff. When it gets up to the receiver, I see both my primary and my secondary pointing in the same direction. I'm going to plot that number as positive. So whatever that number is, I'm going to say it's positive, and that puts me in position A. Look what happens when as I start to move this. So as I'm moving, as I get closer and closer and bring this thing closer, eventually I'm going to get to the following point here where my transmitter, okay, is on the left, and my coil, my receiver coil, is on the right. My transmitter is on the left, so I'm still going to get currents in here, the primary magnetic field, but look at that magnetic field. It's hitting this receiver loop horizontally. So there's no flux that's coming through here, means there's no signal. So that's going to give us a zero crossing. If I do one more step, so my transmitter's on the left and the receiver is on the right, now what I have is something that is, the transmitter's on the left, so I still get my currents in that same direction, and now because they're going to be opposite signs in my receiver, I gotta plot this thing. And then move it farther out. At this point here, I got a transmitter that's right above my target loop. So now I've got zero coupling because of that. And that means I'm not going to receive. And then we'll go on. So the thing that you're going to kind of work out in class is kind of stepping through all of the details of this. I mean, the end curve is like really, really simple, right? But getting there, it's like in the magnetics, getting there, you really need to have your wits about you and kind of think about, okay, primary field in here, so it gives current, they're going to go this way, magnetic fields are going to be up, it's the same for the primary, or opposite, now I'm going to control that stuff. So that's where you're going to be. The last thing just to say is that here's your response curve. So what we showed back here is geometry. All of that's just geometry. When you actually go out into the field, you might be in a position, something like this, where the curves kind of, they'll always look the same, that's the geometry, but let's say the red part here is a higher amplitude than the black, and that's where your response function comes back into play, because now at a particular induction number, you see the red is larger than the black. And if you went the other way, so induction number was really large, you still have the same geometry, it looks the same. It's just that that partitioning between the in phase and the other phase changes, and in here, it's the real part. Okay, so you're going to try to step through that this afternoon. Sagi and I will be there to help you, but trust me, by 5 o'clock, all this stuff's going to see me through it. It's not bad for one day. Okay, thanks.